me to have the opportunity to give a talk here. Also, I want to apologize in advance for my voice. I have a bit of a sore throat, so I hope it will be enough, but yes, it's not at the best, let's say. Okay, so as you can see from the title, today I'm gonna talk about projective general linear groups from a motivic-homotopic perspective. So in particular, I will focus on Nisnevich classifying space and some characteristic classes that arise from the motivic homology of this classifying space. Let me tell first something about the very general problem here. So the general problem is the classification of G-torsors, where G is a linear algebraic group. Over some base field K. Well, of course, this is a huge problem, very general problem, and if we want to tackle it by, let's say, by motivic homotopy means, then of course we have to keep in mind two very important spaces in motivic homotopy that are related to this problem. So the first one is the Nisnevich classifying space. Also called simplicial classifying space, and this is denoted in this way, EG, as in topology, and is defined as in topology. Actually, we take this contractible space, EG, which has a G action, and then we mod out by this right G action. And EG is a simplicial scheme, which on the n simplicial component is just the product of G n plus 1 times. And then we have that boundary maps, and the generis maps are given by partial projections and partial diagonals, so as usual. And then if we mod out in G, in this contractible space, the action of G, we obtain this BG. Now, this classifying space is called Nisnevich classifying space because it essentially classifies torsors which are Nisnevich locally trivial. So we have that homotopic maps from a base U to this classifying space. Homotopic maps, I mean, in the simplicial homotopy category of Morel-Podolsky. So HSK, this is in one-to-one correspondence with Nisnevich locally trivial G-torsors over our base U. Okay, now apart from this classifying space, we have another kind of classifying space in the motivic homotopy environment, and it's called the étale. Étale classifying space. So I will denote this by B with a small at G. And this is defined by this couple of adjoint functors starting from the Nisnevich one. So here I will explain here better. So we can consider the simplicial homotopy category with the étale topology, and the simplicial homotopy category over K with the Nisnevich topology. Here we have étale shiftification, and here we have restriction to Nisnevich topology. And if we start with the Nisnevich classifying space, we étale shiftify and then we restrict it back to Nisnevich topology, then we obtain the étale classifying space. Now, the main heuristic difference between these two classifying spaces is that BG, the Nisnevich one, is more, let's say, topological in nature. It's constructed just as in topology, and it's also, approachable by more topological techniques. Instead, this et al. Classifying space is more algebra-geometric. Actually, it is a model up to a one homotopy as a co-limit of varieties, so sort of infinite dimensional variety. Okay, and this of course classifies torsors which are et al. Locally trivial. So we have the homotopic maps, HSK, and in one-to-one correspondence with et al. Locally trivial G-torsors over U. Okay. Now let me maybe write some very well-known examples. So let's take the easiest base possible, which is just the spectrum of the base field. Then of course there are no non-trivial Nisnevich locally trivial torsors, so it appears that the Nisnevich classifying space is a bit useless in this situation. But of course, if we consider et al. Locally trivial torsors, we get many interesting things. For example, if G is the orthogonal group, then we have that homotopic maps from the point to the et al. Classifying space of ON, homotopic maps here. This is in one-to-one correspondence with, say, n-dimensional quadratic forms. Over K. And for our talk, we'll be more interested in this second example. So if we take projective general linear group, then here we have these homotopic maps from the point to this et al. Classifying space of PGLN is in one-to-one correspondence with the, say, central simple algebras of degree n over K. Okay, so as I said, at least from this, it appears that the et al. Classifying space is the right things to study. And of course, if you have a good understanding of some cohomology theory for some classifying space, then you can produce a theory of characteristic classes and then consider the values of these characteristic classes in the cohomology of the base. And these are invariants of the torsors that you are considering. But now I want to tell a bit more about so the first time that the Nisnevich classifying space was probably considered a bit more also for this problem, and this is in the work of Smirnov and Vishik on subtle characteristic classes. And essentially, they show that in the simplicial homotopy category over the base field K, we have a commutative square of this form. So here we have the map, the initial map from the Nisnevich classifying space to the et al. One. Here we have an homotopic map from the point to the et al. Classifying space, which is actually like a G-torsor X. And here I will call this map alpha X. And this chi X is the Czech simplicial scheme associated to the torsor X. And I denote it in this way, but it's essentially the same construction as e.g. Before for the Nisnevich classifying space. So we take at the n level the n+1 power of X, and then we have that boundary maps and the generous maps are given by partial projections and partial diagonals. But now this object is not contractible in principle. I mean, it becomes contractible as soon as X is a k-rational point, but which essentially means in this case as soon as X is a split torsor. But if you consider non-split torsor, then this object is, this Čech simplicial scheme is not contractible. And in principle, its motivic cohomology is much more complicated than the cohomology of the point. So the general principle here is that, of course, torsors are classified by étale classifying spaces. And we have, I mean, cohomology of the étale classifying space. We can study it and it take values in the cohomology of the point. But we also have that for the same torsor, we produce, I mean, Smirnov and Vishik produced another map from this Čech simplicial scheme to BG, to the Nisnevich classifying space. And now if we study the motivic cohomology of this Nisnevich classifying space, we obtain invariants for the torsors which have kind of values in a more complicated object than the cohomology of the point, which is the cohomology of this Čech simplicial scheme, which is highly non-trivial. So from one side, we get some advantage because, for example, the motivic cohomology of the Nisnevich classifying space is more approachable by topological techniques, is easier to study. Instead, the cohomology of the motivic cohomology of the étale classifying space is not so easy to approach. But on the other hand, we get that this, well, of course, this characteristic classes here take value in principle in something different. So, for example, if we change the torsor, also this cohomology, this Čech simplicial scheme in principle can change, and so we get values in different cohomology rings. Anyways, the work of Smirnov and Vishik was focused in principle on orthogonal groups. So they compute the motivic cohomology of the Nisnevich classifying space of ON with coefficients in Z-mod 2. And this is, as in topology, just a polynomial ring over the motivic cohomology of the point, which I will denote by H, in some generators, U1, UN, which they call subtle Stiefel-Whitney classes. Stiefel-Whitney classes. Okay, and now if we have a quadratic form, say n-dimensional, then we have a map from this HBON to the motivic cohomology of the Čech simplicial scheme associated to this quadratic form. This is actually, well, this is alpha Q star, so induced by this top map here. And the images of these subtle Stiefel-Whitney classes are these subtle Stiefel-Whitney classes for the quadratic form Q. And so these are new invariants for quadratic forms. In particular, they see many things. I want maybe to say something just about the fact that they see the triviality of the quadratic form. So for example, we know that Q is split if and only if UIQ is 0 for all I. Actually, Smirnov and Vishik prove even more that actually this triviality of certain subtle Stiefel-Whitney classes are related to the belonging of Q to certain powers of the fundamental ideal of the bit tree. Okay. Well, how this is proved, maybe I can say a few words about the strategy they use, because it's a strategy that I want to kind of generalize in order to deal with the situation of projective general linear groups. So their strategy of the computation is essentially this. So we have a sequence of this form. So they go by induction, essentially. Then they have a sequence of this form. And this scheme is isomorphic to the affine variety defined by Qn equal 1, where Qn is the n-dimensional split quadratic form. Okay, now there is a decomposition in the triangulated category of motives of Vygotsky, DMK, of this affine variety. So this is just the sum of two cells, so two Tate motives. It's like in topology, it's a sphere bound, it's a sort of a sphere bound. So here we have n equals 2, and then here n minus 1. Of course, we have this bottom cell, which is given just by one k-rational point in it, which splits. And then we have the reduced part of this motif, just this higher cell, this top cell in this pi degree. And essentially this, I mean, by working a bit with this sequence and with this decomposition of the fiber, they produce, well, it induces a Gisin long exact sequence. I don't know where the pen is. Sequence. Okay. A Gisin long exact sequence of this shape. So for motivic cohomology, so something like this. You have H P minus N Q minus over 2 of BON, and it goes to HPQ BON, then the restriction to BON minus 1, and so on. And this is just multiplication by this UN, by this extra polynomial generator. So if you know the cohomology of BON minus 1, then you get the one for BON. Okay, now our situation. Well, the closest thing that I can think about the projective general linear groups is the following. So we have the central extension GM, GLN, PGLN, and we can consider the induced sequence in classifying spaces. BGM, BGLN, BPGLN. Okay, now the cohomology of BGLN is known, it's just a polynomial ring in Chen classes, and the fiber now, well, the motive of the fiber is cellular in the sense that it is an infinite sum of Tate motives, of shifted Tate motives. So since BGM is isomorphic to P infinity, this is the motive of P infinity, which is the same as sum for I greater or equal than 0, T I to I. Two Tates, but this sum of infinitely many Tates. So of course, we don't expect some Gisin long exact sequence, but some Serre spectral sequence, some sort of Serre spectral sequence. So a Serre spectral sequence relating the cohomology of these three classifying spaces. Okay. Yeah. Okay, so I will now present a bit the general result, which is behind this construction. So for a bit of generality, I will need some time, but okay. Let's consider a smooth morphism from a bisimplicial scheme to a simplicial one, a simplicial scheme. And I want this morphism to be coherent. Okay, so now by coherent, it means that if we look at Okay, so x dot n by n to yn, and then x dot n by n yn. And here we have maps x theta, y theta for all theta from n to n. Simplicial map. Then I want this square to be Cartesian. So it means that is Cartesian. So essentially what we are asking is that there is some compatibility between each level of this morphism, and that actually any level can be obtained from below one just by pulling back. Okay, and moreover, we consider a smooth simplicial scheme A dot over K such that so we require first, then pi 0, so pi on the 0 level, it goes from x bullet 0 to y dot. So I require this to be the product of a bullet times y, y0. Okay, I require this pi 0 to be the projection. Is the projection to the second factor in this case. So y here, sorry. Okay, so these are all 0 on the y side. Okay, then notice that I'm asking that pi 0 is the projection, but essentially since there is this coherence thing behind, I'm asking that all the pi I are just projections from x dot I to yi by this Cartesian thing that I'm requiring here. Then as a second thing, I require that, so what? In dmk, the motive of this simplicial scheme here is cellular, is a sum of states. But in principle, it can be infinite. So I have a direct sum for j greater or equal than 0 of some tj, where this tj are direct sum of possibly over an infinite family ij of states in by degree qj pj. And the only thing that I require is that I'm ordering them in a certain way. So where this and the by degree qj pj is less than qj plus 1 pj plus 1. So with this symbol, so it means essentially qj is less than qj plus 1, or qj is equal to qj plus 1 and pj is less than pj plus 1. So I'm ordering these states in a certain way. Okay, this is the second thing. Now the third. For the third, I have to work it. Okay, so let me call by n the motive of the bisimplicial scheme x to y. So this is the motive of pi essentially. in the triangulated category of motives over the simplicial base y dot. Okay. Now, these categories of motives over simplicial schemes have been constructed by Vygotsky, and there are several properties and relation also to the triangulated category of motives over each simplicial level. In particular, we have some restriction maps, functors, sorry, from the triangulated category of motives over this simplicial scheme to the one over the I simplicial component, and n goes to ni. Okay, now essentially it follows from 1 and 2. So from the fact that over each level, this is just a projection, and the fact that actually the fiber is just a sum of states, it follows that, well, let me write it here, and I is isomorphic to the sum from j greater or equal than 0 of this tj in the appropriate triangulated category of motives. So in dn y I. Okay, perfect. Now let me denote by omega n this automorphism. So I do n delta 0, and then I compose with n delta 1 minus 1. And this goes from, so maybe we just call this by this. This goes from n1 to n1. This is an automorphism. I will explain why. So essentially on the base, we have from y1 to y0. So from the first simplicial level to the 0 simplicial level, we have the two boundary maps. So we have delta 0 and delta 1. And they induce some maps between motives in the over the base y0 and over the base y1. So we have in particular n delta I, which goes from y delta I star of n0, and it goes to n1. Perfect. And now by coherence, by the fact that actually all these things, all these squares here are Cartesian, this is an isomorphism. And remember that this n1 in the appropriate dn y1 is just sum of states. So what I'm trying to say here is that actually we are going back and forth, and we have this automorphism of this sum of states. And we can visualize this thing in this way. So okay, maybe let me write here that this is isomorphic to this j greater or equal than 0 of tj. Right now, from vanishing regions in the motivic homology of any Czech any simplicial scheme. So we have that H PQ of any simplicial scheme chi is trivial when Q is less than 0, or and also, well, let me write here, when Q is equal 0 and P is less than 0. So this vanishing of the of any motivic homology ring of some simplicial scheme is actually the reason why we wanted to order the Tate motives in that order that I explained before. Because now we have that this omega n is just an automorphism of this sum of Tates. But if, for example, I mean, we can, maybe let me write it, we can omega n is an invertible upper triangular matrix. Of course, possibly infinite dimensional, but I'm just saying that it looks like something like this. So if we go from Tj to Tj with the same j, then we get to the diagonal and something non-trivial can happen. If we go from small j to big J, then still something can happen. But if we go from big J to small j, then by this vanishing of cohomology, then this part is 0. Okay, so this omega n looks a bit like this, and I mean, is an element of automorphism of n1, right? Satisfying this, I mean, this. Well, we have seen that actually all these automorphisms here are elements here are represented by this sort of matrices. And so in particular, I can consider the J diagonal entry. So I can go from here to the J diagonal entry. And I get just an element omega nj, which now is in automorphism just of Tj. Okay, all of this, which is a bit painful, a bit technical, but just to say that one of the requirements for this theorem, which was the third when I started, is just that our assumption is that all these omega jn, I mean, are trivial. So this is trivial. Trivial, I mean the identity for all j. Okay, so I just want to go in. So this was 3. So actually, apart from the construction, it's just asking that this, well, J diagonal entries of this automorphism is trivial. And then we had the second part, which was the composability of the fiber in sum of states. And then the first part about the projection on the 0 level and all level by coherence. But then if these things are satisfied, okay, then in dm y dot, there is a Postnikov system, Postnikov tower, of this shape. So we have motive n, which was the motive of the total space over the base. So this is just, remember, this is just motive of the total space to the base by this pi, and it goes to T0. And then I get some cone here, and here some map to T1. And then I have N2 and some map to T2, etc., etc. And these are triangles. So these are distinguished triangles in this triangulated category of motives. And of course, as soon as we have a Postnikov tower in some triangulated category, we can produce a spectral sequence. So it induces the spectral sequence of this form. So we have E1 page PQS, which is given by P minus PS, Q minus QS of the base, right? And it converges to HPQ of the total space. Moreover, we have that it is strongly convergent. If for all P and Q, there is L, an integer L such that So the by degree QP is less than QL PL. If I'm saying it right. Yes. Okay, so we get this spectral sequence. It takes information from the cohomology of the base, and I mean, it gives information about the cohomology of the total space, and it's possibly strongly convergent if this extra condition is satisfied. Now, I will maybe say a few words on how I call this kind of Serre spectral sequence. Of course, Serre spectral sequences are defined in topology, and they are available because in topology, I mean, cellularity is available. Everything is cellular in the appropriate meaning. Of course, in the motivic setting, this is not true, so one has to be careful. But maybe the analogy is given by this. So in topology, so for a fiber sequence of this shape, so we have fiber F, and then we have total space E and the base B, such that the fundamental group of B acts trivially on the cohomology of the fiber. So if these things are satisfied, then we get this Serre spectral sequence. Serre spectral sequence, and it goes from the cohomology of the base in coefficients, with coefficients the cohomology of the fiber, and it converges to the cohomology of the total space. So the parallelism is essentially this. Also, in our case, I mean, if we have the right amount of cellularity, so the fiber can be decomposed as a sum of states, then we get this spectral sequence, which has the information, the cohomology of the base, actually, I mean, shifted in the appropriate way by the decomposition of the cohomology of the fiber, and it converges to the cohomology of the total space. And also this triviality condition of the action of P in B, so of the fundamental group of B over the cohomology of the fiber, is a bit recalled by this condition of the triviality of this omega nj. So essentially the fact that something should be consistent, and yeah, well, going from the first simplicial level of the simplicial scheme to the zero. Okay. Right. And I mean, the element produced was in the automorphism of the decomposition of the fiber. Okay, so let's get back to our situation. So our case was essentially this. We recall it BGM, BGLN, BPGLN. The requirements of the construction of this Postnikov tower with the associated spectral sequence is true, is valid for this, since in particular we have that the motif of BGM, as I said, is this sum of dates. Okay, and so in DM BPGLN, we get this Postnikov system. So we get the motif, the motif of BGLN over BPGLN. It goes to just state. T12, and it goes to 2. T24, etc., etc. Okay, these are distinguished. Okay, and this induces the spectral sequence I've said before. Now, notice that this situation is not ideal because, of course, this spectral sequence is more efficient if we have the cohomology, some knowledge of the cohomology of the base and the fiber in order to get some knowledge of the cohomology of the total space. In this situation, we know the cohomology of the total space and the cohomology of the fiber. We are trying to extract information on the cohomology of BPGLN. But of course, even in topology, I mean, not much is known about the cohomology of these classifying spaces because they're, I mean, PGLN is pretty difficult to tackle from this point of view. And yeah, not much is known even in topology where things are easier. Okay, nevertheless, by exploiting this spectral sequence, at least one can say something about the integral cohomology in low motivic weight. This is a bit of a work in progress, so I hope to extend a bit this computation, but well, at the moment I know this. So HP0 of this classifying space, so this is Z for p equals 0 and 0 otherwise. Then in motivic weight 1, we have Z mod n for p equal 1, and there is a canonical generator. So let me write it here. There is a canonical generator X, and actually you can see it from this tower. It's just this first differential going from T to N1, actually N1 shifted by 1, and then from N1 to T1, 3. So it's in the cohomology of the base with, by degree, 1, 3. And it's essentially this generator. So maybe again. Oh, sorry, what's happening? Okay. So this composition is X. Right. So this Z mod n, and then we have K star for P equal 3. Sorry, for, oh no, so this is P equal 3, sorry. And this is P equal 1, of course, yeah, sorry. This is cohomology by degree 3. Okay, and then 0 otherwise. And then we can say something also about HP2. So this is the same as the cohomology of the point for P less or equal than 2. Then it's Z mod n for P equal 3. It's K star times the element X direct sum Z for P equal 4. Then it's 0 for P greater or equal than 7. And then here for P equal 5 and P equal 6, it's not ideal. I mean, still don't have the precise answer. I hope to improve this. So here I don't know. And here I know that there is a Z mod 2 copy, something plus something. I don't know if n is even, and something I don't know if n is odd. But by looking at topology, the guess is that this should be trivial. Should be trivial. So all of this. And yeah, I have an idea of how to prove it. One should consider this second part of the first differential, but I still don't have a reasonable understanding of this composition here. I suppose that it's just 2x, but still not clear to me now. Well, anyways, what I wanted maybe to stress here is that all this differential here, or this composition here, they live in the cohomology with by degree 3-1. So they live in Z mod n. This means in particular that all the challenging part in this computation, so the part that makes this spectral sequence not collapsing immediately, is n torsion. So the challenging. So the challenging part is n torsion. And in fact, if we invert n in the coefficient ring, then we obtain a very easy answer. So we get that the spectral sequence collapses at the second page. So we have the cohomology of BGLN with coefficients in Z after inverting n is the same as direct sum I greater or equal than 0 of the cohomology of BPGLN with the same coefficients, of course, times C1, the first Chern class to the power I. And we know that H BGLN in general is just with any coefficients, is the cohomology of the point, a polynomial ring in Chern classes. So from this decomposition, which is given by the spectral sequence, then we get that the cohomology of BPGLN with these coefficients is just polynomial ring over the cohomology of the point in C2, C3, Cn. So if we kill the n torsion part, then nothing interesting happens. Okay. Okay, yes. So let me finish with a bit of connection of what I said till now with some invariants of central simple algebra. Maybe I will also give the presentation of a possible decomposition of the motive of the Severi-Brauer variety associated with the central simple algebra in terms of this Postnikov system. Okay, first of all, so consider a central simple algebra A over K of degree n. Perfect. Then we have, as I said in the beginning of the talk, we have a map from the cohomology of BPGLN to the cohomology of the Čech simplicial scheme associated to A. And remember that this object, it splits, it becomes just a point as soon as A splits. Okay, so this was called alpha A star. Okay, now we have a knowledge of H31 of Ka. This is actually already present, I guess, in work by Voivodsky and then also Merkuriev, Suslin. I mean, several people studied this Czech simplicial scheme, but this is the same as the kernel. So you can identify this cohomology as the kernel of this map. So the Brauer group of K to the Brauer group of the function field of the Severi-Brauer variety of A. I think it's the right amount of Brauer. Okay. Yes. And then we know that this is generated by the class of Brauer class of A inside the Brauer group of K. And then the class that we found here, the canonical generator X, which was the first differential coming from the Postnikov system, it's sent exactly, well, let me call it XA as, but this is essentially the same thing as the Brauer class. So this this class from the cohomology of this classifying space is exactly the Brauer class of the central simple out. Okay. Okay. Now, so before we had this Postnikov system, which had all this decomposition in terms of Tate motives, and we can restrict the previous Postnikov tower to dm Ka, and then eventually apply the forgetful functor and go to dm, so the triangulated category of motives over the base field. So what I'm doing here, I'm taking this Postnikov system here. This is over BPGLN, and I'm pullbacking over this Czech simplicial scheme of A. Okay. Okay, and so what I get is, maybe I will write just here. I get motive of something which we just write GLN. And then here I have some M1, which goes to KA 1, 2. The N2, which goes to KA 2, 4. Right. Okay. And here, these are distinguished triangles. Okay. Now, what I want to notice is that here, this total space, actually, is XA PGLN mod GLN, which is actually acting diagonally. XA is the PGLN torsor associated to A. So it's a form of PGLN. And I think I wrote it. Okay, yes. Now this is isomorphic to XA times P infinity, so infinite dimensional projective space, mod sum mod PGLN. So as soon as it splits, then this becomes just P infinity. So this is a form of P infinity. It's actually a form of PGL. Okay, the only thing that I want to notice is that sitting inside this variety, there is of course a Severi-Brauer variety, which I think can be thought, though maybe it's not too precise, but I hope it's okay, is an object like this. So as soon as A splits, it becomes PGLN, and then we get just Pn minus 1. And now by truncating this Postnikov system, which is in principle infinite, we get this finite Postnikov tower for this motive of the Severi-Brauer variety, which has this shape. So yeah, maybe they're not exactly the one as before, so I'll probably write something like this. N minus 1 to N minus 2. And here I have k minus 2 to n minus 4. So this is a finite Postnikov system now. Okay, so this gives a sort of presentation and the composition of the motive of the Severi-Brauer variety associated to A in terms of these easier bits, this Čech simplicial scheme associated to the central simple algebra. And well, of course, this, as we said, these splits, they become contractible as soon as they split, and they give, as soon as splits, the decomposition of Pn minus 1 in terms of sum of dates. So T, T1, 2, etc., etc. Okay, I think this is everything I wanted to say. So thank you for your attention. Thank you very much.
Thank you, Fabio. Questions, comments, and you can use the chat if you want.
How does PGLN act on T infinity?
Okay, yeah, this is a very good question also because yeah. So my idea here is that, so you have the action of PGLN on Pn minus 1, but then you can see PGLN sitting inside PGL2n just diagonally, and it acts on, I guess, P2n minus 1. And you can go with PGL3n, etc., etc. So with this diagonal, you get the action of PGLN on this Pn minus 1, P2n minus 1, P3n minus 1, etc., etc. The important part is that anyway you get this colimit of projective spaces just P infinity, this BGM. Yeah, although probably one needs to be careful. As I said, there is a bit of work in progress here, so I'm confident it should work, but with some yeah, doubts.
Okay, other question? So okay, I have a naive question. Does a homotopy invariant property occur in what you have done today?
Yes, there is some which actually was already visible in the work of Smirnov and Dishik, because you need to. So we have this naive map from, for example, in their case was from BON minus 1 to BON. In our case, from BGLN to BPGLN. But from a motivic homotopic point of view, these are wrong. So you need to change them to something which are some sort of yeah, homotopy fibers, this sort of thing. So for example, in the case of so, and that's also the reason why one starts with something geometric of this form. So from bisimplicial to simplicial, because actually we use a model for BGLN, which is homotopy equivalent to this. So times GLN mod GLN, and this projects to, so did I write this correctly? I think so. Yes. Yeah. Okay. So of course, in our situation, we have this naive map from BGLN to BPGLN, but I mean, you cannot study it immediately. You need to move first to some homotopic model, which is this one, which behaves as we prescribe. So if we fix some, so for example, the zero component, it's just the projection, and then you have that there is some coherence, and then also actually Yes, no, yeah, it works. And also that the fiber is actually then just a sum of tates, so it's a simplicial scheme which eventually can be direct sum of infinitely many tates. But yes, there is some homotopy here in dealing with classifying spaces, and which essentially I think hidden in the concept of homotopy fiber sequence, which is kind of the right thing to do. So you move first to something which is more treatable, and then you work with that.
Okay, thank you. So, no?
So naively, the sequence that you're considering for PGLN doesn't really look analogous to what Smirnov and Vishik did for ON. Right? The analogous thing would be to go in powers of a prime, say P.
That's true.
To go from PGLP to the R to PGLP to the R plus 1. Does that not work?
Actually, yes, it was the same. I'm not at all an expert, so I don't know exactly how the fiber should look like in that case. But maybe if it's known, and if the decomposition of the fiber is known, that would be perfect and probably much more efficient. So my very, very basic idea was that I have this essentially tautological sequence for BPGLN, which is given by the definition, and I know that the fiber is sum of tates. So let's try to do what Smirnov and Vishik did, but with infinite tates. But I agree that it's not, I mean, as interesting can it be for, I don't know, generally it's not that good for a computational point of view in this. Well, it gives this decomposition of the motive of the Severi-Brauer variety, which is nice, and well, I think it's nice, but still I don't think that computation is the best. So if one would know the motive of the fiber of the map you suggested, then that would probably better.
Okay, thank you.
Thank you.
I think there are no other questions. So maybe a last one, I don't know. Okay, so this is over for today. So next week there will be a talk on